Hello guys, today we are going to learn about an important question for the B.Tech first year chemistry, engineering chemistry. So this is one of the important questions which are going to give, which we can guess. So let us read the question. They can give in this both ways, that is, explain the energy of a particle in one dimensional potential box, or they can give in another way also, that is, discuss the quantum mechanics of a particle in one dimensional potential box. So let us read the answer. So particle in one potential box. So we all know that this particle, here we can see a particle which is there here. So first let us read the answer and let us analyze it so that we can get a good score in your examinations, which it may be. Let us consider a particle of mass m. So as I have told, there is a particle of mass m here which is free to move along v. So it is free. It can move along v at the x direction, that is, v is equals to alpha. Between x is equals to 0 and x is equals to d. Inside a box bounded by the infinity rigid walls. It is bounded by a wall. Bounded by a infinity rigid wall. So not just a wall but infinity rigid walls. As per the quantum mechanics, as we all know, now we are going to read about the quantum mechanics, and so as per the quantum mechanics, the potential energy V of a particle infinite on both sides. It can infinite on both sides of a box, and inside the box V is constant, that is 0. So we all know it is 0. Okay, thus potential of a box or potential conditions of a box are, if v of x is equals to 0 with limits, then x is greater than 0 and less than d. If v of x is infinity with limits, then x is less than or equal to 0 and it is greater than or equal to d. Let us take it as equation number 1. So in the previous session I have discussed about the Schrödinger equation of a wave function. So according to that, we are going to write the equation as the number 2. The Schrödinger wave equation we have discussed. If you have any doubt, you can go into my YouTube channel and you can search and you can get it and you can clarify your doubt. Apply potential condition, and in the next step we are applying the potential condition which is in this particle, that is v is equals to 0, to the equation number 2. Then we will get, if we apply v is equals to 0, then we guys will get e into psi of x from the 2, and the remaining part will be same. This remaining part will be the same, and here instead of v we are keeping 0. Then e into phi of x will be here. This is written as equation number 3. From the equation number 3, 8 pi square m h square and e are constants. These all are constants. Then how we are considering it? We are considering it as the k square. These constants we are considering it as a k square. This we write as the equation number 4. We substitute this equation number 4 in equation number 3. So after substituting this equation number 4 in equation number 3, we get this equation. This is equation number 5. Then this is a second order differential equation. As we all know, dou square is there, so it is a second order differential equation, and the general solution is, as we all know, we have learnt in the DMEC, that is the max 2 of our second sem. There we have learnt about the differential equation of the first order and second order. By that we are getting to know about the general solution and we are applying it. Okay. So psi of x is equals to a sin kx plus b cos kx. This we are taking as the equation number 6. And the boundary conditions for the particle in one-dimensional box are: at x is equals to 0, psi of x is equals to 0. At x is equals to d, psi of x is also d. Applying boundary to the condition 1 for equation 6. For this equation, we are applying condition number 1. Then we get psi of x is equals to, as here psi of x is equals to 0, when x is equals to 0, then we get the equation in this way. Then the b will be 0, and if we substitute this b in equation number 6, then we get the equation number 7 as psi of x is equals to a sin kx. Applying boundary condition to the condition number 2, as we all know here, let us see, go back. We are applying to the condition number 2 now. Then we get here psi of x is 0 when x is equals to d. We are keeping d in place of x from the equation number 7. Then we get k of d is equals to n pi, because sine 0 is 0. So k of d is also 0, and we are taking k of d as n pi as to the graph which is given here. So k is equals to n pi by d. We are taking this d to this side, from left side to right side. When it is multiplied, then we take it into our right side, then we get the multiplier will get the divisor, and we are squaring it on both sides. When we square it, k square is equals to n square pi square by d square. This is equation number 8. If we see the before equation, which is the k square here, see here k square. So this k square and this k square, we are comparing this both k squares. So after comparing this both k squares, then we get here pi square will be cancelled, and we get the equation from the E. This is the energy equation of a particle. Then n is equals to, it may be 1, 2, 3, 4, 5, 6 and so on. It may be any number. So we can't consider n is equals to 0. We can't consider it, because wave function is a 0. As the wave function is 0, then how can we consider n is equals to 0? Okay. Hence, the energy of a particle will depend upon the length or distance of a box. Some of the energy levels are we can see here for n is equals to 1. When we take n is equals to 1, if we apply E from here, we take E from here, E1 is equals to h squared by, here n is 1, so 1 square is 1 by km d square. Km d square. Here E1, we can see E1 here, which is only of one line. And N2, when we take n is equals to 2, then E2 will be, so in this way. So for E1, even. So in the n is equals to 2 we are going to draw the lines. You can see here, when n is equals to 3 we are going to get n even, and in n is equals to 4 we are going to get 16 even. Okay, we can do it. N is equals to 5, 6, 7, 8 and so on, but we don't have that much time now, so I am continuing by observing the energy diagram. Here we can see the energy diagram, which is here. In even we are going to get only one line. In here in n2 we are going to get 4 lines, here 3 lines, here 4 lines. So in this way, as the n value increases, the lines also increases. These are the energy levels. So by observing the energy diagram, the energy levels are discrete. In general, according to classical mechanics, the energy levels are continuous, whereas according to the wave or quantum mechanics, as here we are reading, in classical mechanics levels are continuous, whereas in wave and quantum mechanics these energy levels are discrete in form of small packets. Why they are discrete? Because of the small packets. These packets are called as quantas. These packets are called as quantas, i.e. its energy is quantized. Therefore, particle in one box possesses quantized energy, but a 3 particle does not. So by this we can understand this equation, and we can understand this derivation, which is a particle in one dimension. This is quantum mechanics. This is a topic from quantum mechanics. This is one of the important topic, and I am again telling, please like, share, subscribe, comment if you have any doubts, or if you want any another topic, then I will do a video. Please comment it below. Okay, bye.